We're going to look at how a tripeptide is made quickly. Not really part of this course. You really focus on it in 242. Tripeptide would be a 3 amino acid protein, and it comes from the amino acids. These are generic amino acids. There's the variable R1. With alanine, it was a methyl. And we're going to see with aspartic acid, ASP, it's a CH2CO2H. And with, let's see, lysine, it's a butyl with an ammonium on the end. So what's happening here is these 3 amino acids are being connected in a special reaction. This O is lost right here. And if you look at it, NH3 is really N with 3 H's, right? We'll put 2 of them in red and 1 of them in black. And highlight the 2 red H's and look at what happened when they got connected. There's 1 of the H's still, there it is. And what's missing? What got removed when these 2 molecules came together and made this bond? Well, 2 protons, yes, and an oxygen. What do you call that? It's H2O water, yes. And we did the same thing over here. I'm not going to draw it again. This O minus and 2 of the H's here. And in biology, they call that a dehydration synthesis. Chemists don't really like that choice of words. Well, this chemist in particular. It does describe what's happening very well. But as a chemist, I know that in almost every biological dehydration synthesis, it's the synthesis that happens first. And then a dehydration at the end to lose the water. So that would have been a better name. So why didn't they call it synthesis dehydration? The same reason my mom didn't call me Todd David Whitaker. She's going to be loving this video. She liked the sound of David Todd Whitaker better. That's the reason. And I go by Todd. So there you go. TMI, I know. All right. So in chemistry, we prefer the one-word answer of condensation. Condensing implies bringing things together, right? And you also spit out a small molecule like water. It's almost always water, but not always. And we did how many condensations to get from these 3 things to this 1? 2. 1 condensation there, another condensation there. So that's why I made 2 waters. You always get 1 less water than you have amino acids because you're not condensing the end. Okay, so we made a tripeptide. What I did here was gave you a picture of a fully protonated form of this tripeptide, ALA-ASP-Life. That means the one on the left is alanine, the one in the middle is aspartic acid, and the one on the end is lysine. And these pKa's I give you on the test. The fully protonated form, and the picture is for the molecule at a pH of less than 2.2. Because the lowest number of all the 4 numbers is 2.2. You see it? For this thing to have its proton, the pH of the environment must be below 2.2. If you think about it, what does low pH mean to you, even if you don't have an acid-base background? If somebody says the pH is low, what kind of environment are they talking about? Acid. If the pH is high, what environment are they talking about? Base. Now I'm talking about the environment having a pH and your molecule having pKa. If your environment has a higher pH than the molecule's pKa, the environment is basic, like you just said. So above 2.2, this will lose its proton and become O minus right here. Okay? And this exercise we did this morning was 2.2 is below every one of these numbers. Do you agree? That's why they are in their protonated form drawn here. Carboxylic acid has its proton. Ammonium has its proton. You go above 2.2, like 3, the environment's now more basic than the 2.2. It loses its proton. All the other ones keep theirs because the environment's not basic enough to take anything that's not above, that's above 3. You can only take things below 3. Now, if you go to 5, you're also going to grab this one, right? Look at it, it's gone. If you're at 11, now you grab everything. I jumped. There's a molecule in the middle I didn't go to where I could have gone to pH 10.0, and this one would lose its H, and this one would keep it, right? But I was running out of room on the page, so I just jumped to the last molecule. 11 is above every number. That means every acid loses its proton. When the environment's more basic than your pKa, you lose your proton. When the environment is more acidic than the pKa, that's to say it's lower than the pKa, you get your proton. Fully protonated form has the environment with a pH less than all the numbers. Fully deprotonated form has pH above every one of the numbers. Right here. 11 is above all 4 of these numbers. And there's the story. So on the next page, when we do our activity, you're told you're going to start with the diprotonated form. This one's the tetraprotonated form. It's got 4 protons. This one's the triprotonated form. This one is the di. Here they are. 1 proton left here, another proton left there. We good? We're going to go to our activity. Now I've got the diprotonated form of ala-asp-lyse. And the question is, it's the same question as before. I didn't copy the parts A, B, C, D, E, connect the conjugates, put the pKa's and the pKeq's, et cetera, et cetera, et cetera. We're going to do them all. But before we do that, we do something else. What is that? Before you start. Cross off the spectators. There's 2 of them there. Replace the charge. Put it on the O, please. It does not belong on the left side of the molecule. The charge is on those O's. Which one of those 2 is the acid and which one's the base? The one on the right is the acid because it has an extra proton. Extra proton is the acid, pKa. Missing proton is the base, pKb. pKa of bicarbonate. Hey, I think this is the second time today. This is the form you might recognize more quickly. HCO3 negative. It was 11, wasn't it? If this is an acid, what does an acid react with? A base, the conjugate base of that. We got to pick the right numbers to use, everybody. Okay. If this is a pKb, what's it reacting with? An acid or a base? An acid. We have to pick, and you've done this exercise already, which of these 2 numbers of the remaining acids reacts first? The lower number. The only number that's relevant is the 9.9. pKb, 14 minus 9.9. Do 14 minus 10, you get 4. Subtract well, it's more than that, 4.1. Add 1.1. 4.1. Not a strong base, not a strong acid. Both are positive. Okay, well, the thing is, you got to show me what the species looks like after losing the proton that was 9.9. And I know you don't want to draw the whole molecule. You are allowed to use short forms, but only if you do them accurately. I'm going to get my purple pen. I'm going to circle everything up to, but not including the NH3. Everything. Up to, but not including the NH3, and I'm going to call everything in that circle R. So you're going to write down R is attached to, what does NH3 become after it loses H+? NH2 with a pKb of 4.1. Yes. Yes. And why am I circling this one and not the one below it? It's all based on pKeq is the left acid minus the right. Negative 1.2, is that right? No, 1.1. I don't know where the 2 came from. Yeah, 1 is, negative 1 would be, yeah. Is that right? That's right, isn't it? Yeah. Okay, and the KEQ, better favor the right side. 10 to the positive 1.1. Yep. Just a little more than 10. Maybe 20. 20 of these for every one of those. So if you compare to the morning lecture, we only switched these two, and that changed this to a base. So it was a whole different ball game. You definitely want to watch the morning video too. You always do. And I think that's all we have. And all you need to copy is what you see here. And I'll leave you up to that.